I've been building this little computer based on the 6502 processor, and we had it successfully printing out Hello World. But that was with this really slow clock module. And so in the last video, I replaced that with a 1 megahertz oscillator like this. But when I did that, it doesn't work anymore. If we reset this, it doesn't display the message. And I know a number of you who are following along with these videos, maybe you got the kit from my website, so you have all the parts. I know a number of you were having the same issue. And I teased a bit at the end of the last video that this is because the LCD takes a little bit of time to execute each instruction. And at 1 megahertz, the processor is just going too fast. So let's see what we can do about that. Well, what's happening is, if we initially power up the computer, and initially you can see the LCD is not initialized. It defaults to this one-line mode that looks like this. But when we reset the processor so it starts running our code, we see that the LCD appears to get initialized, or at least it goes into this two-line mode and the cursor shows up, but nothing else happens. And I think that's because the very first instruction we send to the LCD is this initialization instruction that sets the interface into 8-bit mode, sets it to two-line display, and selects the right font. But once our code sends this instruction, it takes the LCD a bit of time to actually do the instruction. But our code just keeps going and sending all these other instructions before the LCD is ready. And in fact, I think we're sending all these instructions and the entire hello world message while the LCD is still processing, this first instruction up here. And if we look at the datasheet for the LCD module, you can see it warns us about this. It says when an instruction is being executed for internal operation, no other instruction other than busy flag address read instruction can be executed. So once we execute this first instruction here, the LCD isn't going to do anything else while it's busy. And so you might think, well, wait a minute, the cursor's showing up on the screen, so doesn't that mean that the next instruction that turns the cursor on is running? And honestly, I'm not sure. Maybe, it might also just be that the cursor's on by default. If you look at the datasheet, you can see it says each of these instructions that we're doing takes 37 microseconds to execute. And at 1 megahertz, 37 microseconds is going to be 37 clock cycles. And if you look at what we're doing to execute each of these instructions, we're loading something into the A register, and then we're jumping down to this LCD instruction subroutine, which is down here. And this sets all the right control bits or whatever to send the instruction. Well, all of this code, if we look up, the instruction cycle times for each instruction, it turns out all of this code takes about 35 clock cycles. And so that means it ought to take about 35 microseconds. So we're going too fast, but maybe only barely. Now, one trick, if you want to add just a short delay, is to put some no-op instructions in here. Now, each no-op instruction takes 2 clock cycles. So, if we got 5 no-ops, or actually, we can go ahead and put 10 no-ops in here. That ought to add about 20 microseconds of delay. So let's see if this works. I'll save this and run the assembler. I'll get the EEPROM out of the circuit and put it into the programmer. And then I'll reprogram the EEPROM. And there it goes. And I'll just speed this up. And there it is. It's done. So now if we put the EEPROM back in the circuit and power it back up, reset it again, make sure it runs the program, and it looks like the same thing. So what's going on? So now with these no-ops, the entire process of sending an instruction should now be taking about 55 clock cycles, because I figured out that it was 35 clock cycles just to execute the code that we had. Plus we added these 10 no-ops, so that should add another 20 clock cycles. So the whole thing is 55 clock cycles, which at 1 megahertz would be 55 microseconds. And I would think that if the execution time of each instruction is only 37 microseconds, this ought to work. But I don't know, maybe we need a little bit more delay. And of course we can add more delay by adding more no-op instructions, right? Each instruction gives us another 2 microseconds. So we could go to 20 no-ops, and that'll take 40 microseconds, which hopefully will be enough, because that means we do all the stuff we need to do to send an instruction, then do nothing for 40 microseconds. Remember, the datasheet says each instruction takes 37 microseconds to execute. So we do nothing for 40 microseconds, and then we begin to set up for the next instruction. So let's try this out. I'll get the EEPROM in here and reconnect power and hit reset to start the program. And that still didn't work. So, in principle, there should be some amount of delay we can have that will make this work, right? Because we had it working with this slower clock. And of course, this was like 5 orders of magnitude slower, but still, at least in principle, adding some delay somewhere ought to fix this. Well, I won't bore you with the whole thing, but I kept adding no-ops and kept adding no-ops until I finally got it working. And it took a lot more than I expected. Apparently 700 no-ops still wasn't good enough, but 750 did the trick. You can see if I power it up and hit reset, there we go. Now, why I would need 750 no-ops or 1500 microsecond delay is not entirely clear. So one thing I noticed in the datasheet is this note that says, to be sure that it's not in the busy state before sending an instruction, also says that if an instruction is sent without checking the busy flag, the time between the first instruction and next instruction will take much longer than the instruction time itself. So it says, yeah, the instruction times are in table 6 here. So these are the how much time it takes to execute each instruction. But if you don't check the busy flag, then it might take much longer than that. And I don't know, that seems weird to me. Why would not checking the busy flag make it take longer? So it seems kind of strange. And the other thing I noticed is that 750 no-ops will give us a 1500 microsecond delay, and 1500 microseconds is 1.5 milliseconds. And so this return home instruction jumped out to me as taking about 1.5 milliseconds. But, we're not using that instruction anywhere in our program. So initially I didn't think anything of that. We're doing function set, which is 37 microseconds, display on-off control, which is 37 microseconds, entry mode set, which is 37 microseconds, and clear display, which is suspiciously missing an execution time. So maybe this clear display is actually taking, 1500 microseconds. Who knows? But whatever's going on, one thing's for sure, nobody wants a program with 750 no-op instructions in a row like this. There's got to be a better way. And of course, the better way is to do what the datasheet tells us we should do. We should check the busy flag and wait until the LCD isn't busy before sending it the next instruction. So how does that work? Well, one of the instructions here is to read the busy flag and address down here at the bottom. And like all the other instructions, the register select is 0 to indicate that it's instruction, but the read-write bit is set to 1 because we're reading. We're not sending an instruction to the LCD like all these other things. So we're actually reading data from the LCD. And when we read, we're going to get an 8-bit value, and that's what this is here. And 7 bits are this sort of address counter thing, but the top bit is the busy flag, and that's what we're looking for. So let's write some assembly code to read that. So first things first, let me get rid of all these no-op instructions, highlight these and jump down to the bottom of this block here, and I'll just get rid of all that. So there we are, 750 fewer lines. All right, so to read the busy flag, maybe I'll make another subroutine. We'll call it LCD wait. And then we can call this subroutine and it'll just wait until the LCD isn't busy and then return. And so to read the busy flag, we need to set register select to 0 and the read-write flag to 1. So I'll load that into the A register. Just the read-write bit is set. And I have these symbols defined up here at the very top. Go all the way up here. So the read-write flag is, I've got a symbol set for that. So back down where I was, I can just say RW to get just the right bit set. So that's in the A register. And then if we do a store A, port A, that'll put that value out on port A of the 6522 interface adapter. And port A is these first 8 bits on the left, which I've really only got 3 bits hooked up for the register select, read write, and enable bits. But anyway, this will set those bits so that we're ready to do this read operation. And then like any of the other instructions here that we've been doing, to actually perform the operation, we have to toggle the enable bit high. So I'll load A, and I want to keep everything else the same, so I still want the read-write bit set, but then I also want the enable bit set, so I'll just OR those together so both bits are set. And with that in the A register, we can put that out on port A of the 6522 by doing a store A, port A again. And now that toggles the enable bit high to actually do the read. So now the LCD will be outputting whether the busy flag is set or not, along with this address counter thing. And that'll be output on the 8 data bits, which are hooked up to port B of the 6522 here. So if we go back to our code, we can load A from port B. And that'll read from port B, which is hooked up to those data bits, and put the contents into the A register. Except for one problem, actually. Everywhere else we've been writing to port B. So, we're storing A to port B. And down here where we're printing the character, we're storing A to port B. So everywhere else we're writing to port B because we're writing information to the LCD. We're not, this is the first time we're actually reading something from it. And to do that, at the top of our program, we had to set all of the pins on port B to be output pins by writing 1s to the data direction register for port B. Well, now that we want to read from port B, we want to sort of turn that around, at least temporarily, down here in our new subroutine. So come back down here, and before we do any of this stuff, I want to set the direction of port B to input. So I want to write all 0s to the data direction register for port B, so to set that as input. And so I'll write that to DDRB, that's the data direction register. And DDRB is just an address. It's defined up here at the very top as 6002. And in a previous video, we hooked up this interface adapter chip, so it's enabled for those 600 whatever addresses. So this will set port B as input down here. And then, we can just copy this, and at the end of whatever it is we're doing here, we can set it back to being output again. So I'll just add that down here. Okay, so we're setting port B to input. Then we are telling the LCD we want to read the busy flag. And then we're toggling the enable flag on to actually execute that read. And then we're reading the result from port B into the A register. So once we do that, we've got the busy flag in the A register, and we just want to check if it's set. And if it is, we want to loop back up to I guess up to here, and just sort of keep going through this loop of all this stuff, and just keep reading it until it isn't busy anymore. So how do we do that? Well, we're going to need some kind of conditional jump or branch instruction or something that will loop back up to the top of our subroutine if the busy flag is set. But then continue executing something and maybe return from the subroutine down here at the bottom if it's not set. And the 6502 gives us a bunch of conditional jump instructions, which are all these branch instructions here. You can see there's branch on carry clear, branch on carry set, branch if equal, branch if result minus, not equal, plus, branch on overflow clear, overflow set. There's a lot of different conditional branching instructions, but what do they all mean, and which one can we use to branch to one part of the code if the busy flag is set from the LCD, and a different part of the code if the busy flag isn't set? Well, the key to understanding these different instructions is that they all work off of different CPU flags. So internally in the 6502, there's a processor status register that stores 8 bits of status. And some of these, reflect different modes that the processor might be in, but relevant to what we're doing, there are a few bits that are updated by certain instructions. So the carry flag, the 0 flag, the overflow flag, and the negative flag are all potentially updated by different instructions. And if we go look at the different instructions, actually a different table here somewhere, there's this column out here that shows what processor status flags, register flags are updated. So for example, this add with carry instruction here, the first instruction, add with carry will update the negative flag, the overflow flag, the 0 flag, and the carry flag. So anytime you do an addition with this instruction, all of these flags are going to be updated based on the result of that addition. Like, if you're trying to add 2 numbers and the result is more than 255, the answer is not going to fit in 8 bits. But the processor could set the carry flag, for example, to indicate that. And then you could use a branch if carry set or branch if carry clear instruction to do something differently in each case. Now, one instruction that turns out to be really useful here is the compare instruction. And what it does is basically subtract something from the A register and then ignores the results. So it doesn't change what's in the A register, but it does update the status register as if it had done that subtraction. So let me give you an example. If we did compare 42, this would compare whatever's in the A register to 42. But really what it does is it subtracts 42 from whatever's in the A register and doesn't do anything with the result, but it will set the status register as if it had. So if the A register had 42 in it, like if we did a load A 42 beforehand, then this is going to be the same thing. Well, this compare 42 is going to subtract 42 from 42, which is 0, and it doesn't put the 0 anywhere, but what it does do is it sets the 0 flag. So the 0 flag would be equal to 1 after this compare. But then there's this branch if equal, where is it? There we go, which will jump if the 0 flag is set to 1. So if the 0 flag is set, then it will jump. And you can see why it's called branch if equal, because this will compare the A register to 42 and then jump if the A register equals 42, right? So if we said branch if equal to some address, then it's going to branch to that address if the A register equals 42, because we would subtract 42 from 42. We don't do anything with the result. We set the 0 flag, but then this branch if equal instruction looks at that 0 flag and says, that's set. I better branch to that instruction instead of continuing execution. So the name sort of makes sense, branch if equal, after we compare something, but it's useful to know that the way it really works is by simulating subtraction and then branching if that 0 flag is set. But anyway, back to what we're trying to do. We've read this busy flag into the A register, and now we want to figure out if it's set. Now we can't just check if the A register is 0 or not, because only this one bit is the busy flag. The rest of these bits are the address counter, and who knows what they're going to be, and we don't really care. So what we can do is use the AND instruction to do a bitwise AND with the one bit that we actually care about. So for example, if we read this into the A register and we get, this, whatever binary thing, the busy flag is set, but we don't care about all this other stuff, we could AND that with 10000000, and then the result will just be the logical AND of each bit. So if this bit and this bit are set, then the result is going to have that set. But for every other bit, since these are all zeros, you would never have a situation where this bit and this bit are set, because this bit will never be set. So we're basically zeroing out all these bits except for the top bit, which is the busy flag. So by ANDing with this value, we're basically zeroing out all of the bits except the top bit, which is the busy flag. Which means that after this, now the entire value will either be 0 if the busy flag isn't set, or not 0 if it is. And just to double check, we can see that the AND instruction does in fact update the 0 flag. So we could use that to conditionally jump to stay in a loop until the busy flag isn't set anymore. So let's do that. So here, after we've read the busy flag, we're ANDing it with 1000 just to pick out that top bit to zero out all the other bits. And then this AND will also set the processor status 0 flag, depending on whether the LCD's busy flag is set or not. So that means we can do branch if equal, because branch if equal is going to look at that 0 flag, and we can jump back up to LCD wait. Although, wait a minute, is this right? Let's think this through. So we want to stay in the loop while the LCD is busy. So if the LCD is busy, then ANDing like this to pick out the busy flag will be non-zero. So LCD busy flag is set, then that means the CPU's 0 flag will not be set. So we want to stay in the loop while the LCD is busy. So that means we want to stay in the loop while the 0 flag is not set. So really we want branch if not equal, since that'll branch if the 0 flag is not set. So there we go. And I don't know, I find this a little bit confusing because the AND here is picking out this bit that we care about, but then the branch if not equal really means we're branching if this bit is set, right? So maybe in this case, maybe it makes more sense to think about this as branch if not 0. But anyway, this ought to stay in that loop, or I guess sort of create this loop that'll just keep looping until we read the busy flag and it's not set. Once that happens, then we just need to sort of clean up down here. We're already setting port B back to output, but we should also clear the enable bit. So I can do that by just copying this down here, since that'll turn off the enable bit. And so now this ought to ensure that everything's cleaned up before we return from the subroutine. So now we should be able to use this in our LCD instruction subroutine. And this is the subroutine that sends an instruction to the LCD module that we did in previous video. So before we send the instruction, we could just do a jump to subroutine, LCD wait. And this will then go up to our LCD wait routine and wait until the busy flag isn't set before continuing with the rest of whatever it does to actually send an instruction. The one thing to be aware of is that the LCD wait subroutine we just wrote uses the A register, right? We're loading things into the A register here. We're reading that busy flag into the A register. So this is actually going to be a problem because the LCD instruction subroutine sends an instruction to the LCD, but the way it works is the instruction it sends is whatever was put in the A register before calling it. So up here, we put something in the A register, we call LCD instruction, that jumps down here to LCD instruction, and we actually depend on having that thing in the A register in order to send it as an instruction. Well, if LCD instruction immediately calls LCD wait, and LCD wait clobbers what we had in the A register, then that's going to be a problem. So what we can do is in our LCD wait subroutine here, we can just push the value from the A register onto the stack at the beginning and then pull off the stack into the A register at the end. That way the A register will be back the way we found it. Except we have to be careful here in our loop that we don't jump all the way back up to the top here and push something else onto the stack. We only want to push one thing onto the stack at the beginning of the subroutine and then pull it off at the end. So maybe I need to add another label here. So like LCD busy, and then here we'll jump to LCD busy. And in fact, I can even move this down a bit because there's no reason to keep setting port B to input. We only need to do that once at the beginning, and then we're setting it back to output here at the end. So this ought to work, I think. We push the A register onto the stack, we set port B as input, then we do all this stuff to read from port B. We check if the busy flag is set, and if it is, we loop back up to LCD busy here and just keep checking. And then once it's not set, we stop reading from the LCD and set port B back to output, pull the original value in the A register off the stack and put it back in the A register, and then return from the subroutine. And so we're calling that subroutine right here before we send an instruction to the LCD. And maybe we should also do it before we print a character to the LCD. So anytime we're doing anything with the LCD, we check to see that it's busy, or we wait, I guess, until it's not busy before sending it, either an instruction or sending it a character. So let's try this out. I'll save it, Run the assembler again. I get the EEPROM back into the programmer. Run the assembler. There it goes. It's programming, and I'll let this, I'll speed this up a little bit. And it's done. So now let's put this EEPROM in. So get that one out. This is the one with the new program. Put that in. And then I'll power this up, reset, and there it goes. It's working. So that's awesome. Now, at this point, I'm actually curious if this is faster or better in some way than what we had before with the 750 no-ops. I mean, obviously, aside from the ridiculousness of the code with 750 lines of no-op. So I have that program with all the no-ops on this other EEPROM here. And of course, I have the program that we just wrote here that checks the busy flag on this EEPROM here. So we can sort of compare them. So let me put this other one back in there real quick. Power this up. And of course, this one works too. This is the one with all the no-ops. And I think what we can do to kind of see how fast it's running is take a look at the enable pin on the LCD, because for each instruction or character or whatever we're sending to the LCD, we're toggling that enable pin. So if we look at it, we ought to be able to see sort of the timing of everything. It looks like I maybe bounced the enable pin a couple times, got a couple exclamation points, because that, I guess, was the last data that was on there. But anyway, we'll reset this. And so now this is set up to look at that enable pin. And so I'll set the oscilloscope here to single shot and trigger here somewhere. So it should start capturing once the enable pin goes high. So let me hit reset and run the program. And there we go. You can actually see the 4 instructions that we're sending with the 1500 millisecond or so delay between each one. Actually, I guess it's a little bit longer than 1500 milliseconds because the no-ops are adding 1500 milliseconds, but the actual sending the instruction itself is another, what do we figure, like 35 microseconds. And then I guess this stuff out here, actually we can zoom in here, so we can see our instructions. And then if we go all the way over here, this is probably the message itself. That looks like it should match the 13 characters that we send to print our hello world message. So okay, let's compare now the new program that checks the busy flag. So I'll disconnect power here, get this EEPROM out of here, put the other one in, power back up, reset. Yep, that's still working. But now let's re-trigger the scope here. So get out of here, go back to single shot mode, and then I'll reset the computer again so it reruns the program. And look at that. Definitely it takes less time overall to run. I haven't changed the scale here. But let's actually zoom in there and take a look at what's going on. So I'm just guessing here, but it looks like we've got our function set and then, or actually we check the busy flag and then function set, then check the busy flag, and then this would be display on, check the busy flag, and then, set the increment mode, and then display on and clear the screen. And then it looks like it's probably just continually checking the busy flag. So I guess it's that clear display instruction here that takes forever, because then it's checking the busy flag, and so on until it gets here, and then here it looks like it's probably just sending the message, because that's the next thing it would do, and that's checking the busy flag between each character. So I guess it really was the clear display instruction, because we've got 1, 2, 3, 4 instructions. And it's that 4th instruction that then we get stuck in this, or not stuck, but we're in this loop for a while where we're checking the busy flag before we can print the message. So I don't know about you. I think that's pretty cool to see. We've got our Hello World program working again, and this seems like the right way to do it. Really, the only other thing we could do to improve this is we go back to the code. This part where we actually print the message. It's kind of annoying to have each character individually sent like this. It'd be a lot better if we just had a loop that printed out the whole message. And the way to do that is, right now we're loading each character into the A register directly and calling printChar to send it to the LCD. But instead of using this load immediate syntax with the hash sign here to load a character, we could have the character somewhere else in memory and load it from there. So for example, somewhere else in memory, say, down here, I can add a label, so we'll call it message, and then just put a byte, which I can still represent as a character like this. And then instead of directly loading an H into the A register, like we're doing up here, I can do load A message, and that will load a byte from the address referred to by the labeled message down here. So that's going to load this H down here. And of course, that's not much better. But the other thing I can do is instead of just having a single byte down here is I can actually have a whole string. So if I change this instead of byte to ASCII Z, I can put the whole message down here. And what this does is it says at this point in memory, referred to by this label message, sort of after this jump loop instruction and before the the LCD wait. It's just going to put this string right there in our binary output. It's just going to insert this string, and the Z in ASCII Z means that not only will we have the string in memory, but at the end of the string, there'll be an extra byte that's just a 0. So actually, let me save this and assemble it real quick. So run the assembler again, and then do a hex dump of the output to see what's in the assembled binary file. And here you can see the message, hello world, is right in there. And at the end of the message, this byte here, so this will be the LD exclamation point, you can see there is a 0, a null byte. And then after that, we have the 48A900, which actually corresponds to the push A and then load A00, which is just the code that comes after this. So this message is here, and then there's just push A, load A0. So it's just kind of jammed right in the middle of this code. But that's fine, because we have a jump here, and then this is the beginning of a subroutine. So this isn't really in anyone's way. But we have this this message here it's going to be in our ROM. It's going to be at an address that we can refer to by this label message. But anyway, up here, we've got this thing where we're loading a message. And of course, this is still only just going to load H into the A register because the A register is only 1 byte. So it's just going to load that first byte. But then what we want to do is, print that character and then somehow load the next byte. So we always want that, so the address of message +1 or something like that. And then this would be, the address of message +2 and so on. We could do something like that. Unfortunately, this doesn't work written quite like this, but there is a way to do it with the X register, which is sort of the index register. So if we say load a message, X, that means use the address of message, because message, remember, is pointing to some place in ROM, which has this message. So use the address of that and then add whatever's in the X register. So if we set the X to 0 up here by doing load X 0, then if we add X here, X is 0, this is going to be the same thing. So we're just loading message. But then if we do an increment X and then load a message, X here, then this is going to load message +1 because X started as 0. We incremented it to 1 here. And we could sort of keep doing that, right? So increment X again, load a message, X. This is now going to be, message +2, right? Because X started as 0, we incremented it to 1, incremented to 2. And we could keep going. But now we've actually got something that's a bit easier to make a loop out of because we're doing the same instructions over and over again. So what we want to do is we want to load the current character of the message into the A register, call the subroutine to print that character, increment X, and then jump back up sort of to the top of this block to print the next character. So I can just say jump print or something, and then put a label here, call it print. And then this will, sort of start with the first character in our message, print that, increment it, and then jump back up here and print the next character and so on. And that means I can get rid of all of this other stuff that we were using to print hello world, character by character like that. Get rid of all that. So now we have our message down here, hello world, and we have this little block of code here that will sort of loop character by character and print them all out. The only problem is it won't actually ever stop because this just always increments X and it always jumps back up to print. And so it'll start printing hello world to the LCD, but then it's going to keep going past that 0 and into this code here. It's actually going to be printing sort of whatever character representation it can come up with for this code to the LCD, which I don't know, might look kind of interesting, but it's not what we want. So in order to stop printing when we get to the end of our message, we can take advantage of the fact that this ASCII Z thing is putting a null or a 0 byte at the end of the message. So here, after we load A from the message plus the X offset to get the next character in the message, it turns out that the load A command will set the 0 flag if what it loaded was a 0. And that's great because the branch if equal instruction will branch only when the 0 flag is set. So we could just say branch equal to loop, which will just sort of branch right down here to this loop after we're done printing. So if we just loaded a 0, meaning we got to the end of our message, then jump out of our print loop here down to just our little infinite loop that we kind of run when we get to the end of our program. So I think this ought to work. We initialize the X register to 0, and then we go through this loop where we're incrementing X and printing each character in our message until we load a null byte, which tells us we got to the end of the message. So let's try it out. Save this, and again, run the assembler. Disconnect power and get the EEPROM back in the programmer. Then this will run the programmer. So there we go. We're programming that onto the EEPROM. And now let's see if this works. And look at that, power's right up, hello world. And there it is, 9 videos into this adventure, and I think we finally have a hello world program that I'm happy with. And now it's pretty easy to make it say something else. So I can just come in here and edit this message to say whatever we want. And the thing about the LCD module, it's got 2 lines, and the way it works is that each line, is 16 characters long, but internally each line is represented as 40 characters. So if you send it something that's longer than 40 characters, character number 41 will show up on the second line. So here in my editor, let's see, my string starts at column 19, it's saying. So if I go out to column 59, that'll be 40 characters into the string, so I can add some more text that'll appear on the second line of the display. So let's try that. I'll save this and reassemble and reprogram the EEPROM. So let's put the EEPROM back in and we'll power it up. Reset, and there we go. So at this point, I'm going to officially say I'm done with this Hello World program. Though there are definitely at least a couple more things I want to do with this 6502 computer in future videos. So if that interests you, I'm sure you can figure out how to tell YouTube to tell you when I release a new video. And you can still get kits with parts for any of these projects over at my website. We've got all the parts in stock and we're still able to ship, but because of the shutdowns right now, everything's taking just a little bit longer, maybe a week or so right now. But check eater.net/shop for the latest on that. And as always, thanks to all my patrons. Your support is a big part of what enables me to make these videos, so thank you.